Good afternoon, everybody. Thank you for attending my session, Lifecycle Inference on Unreliable Event Data. My name is Allshouse, and I'm here on behalf of BitSight. We're a company headquartered in Boston, Massachusetts that pioneered a new cybersecurity market known as security rating services. And I'm going to talk to you today a little about some of the data processing and analytic challenges that I, as a researcher, face in this market, as well as some Spark DataFrame's tradecraft for addressing those challenges and ultimately deriving some value out of some otherwise difficult to deal with data. Before I outline the talk, I'll tell you a little bit about myself. I spent the bulk of my career at the US Department of Defense, where I served in a variety of roles and capacities. About 2 years ago, I made the transition to BitSight, a pretty dramatic transition from giant government bureaucracy to small tech startup. But I currently serve there as a security research scientist tasked with developing novel methods of measuring and quantifying cybersecurity risk. Towards this objective, I do a lot of analysis on a variety of data feeds, some internally collected, some obtained through various data partnerships, and ultimately doing analysis on these feeds, looking for correlations as well as other potential signals of risk. I rely heavily on Apache Spark for this workflow, since it provides a lot of flexibility and it's fairly data source agnostic. It really helps facilitate doing this type of analysis across various large data feeds. And of course, it scales to whatever data volume that I'm typically dealing with. So with that out of the way, I'll tell you what you're going to hear about today. I'll give you a little bit of background on what security ratings are, since it'll provide context for some of the analytics and tradecraft that I'm going to be describing later on in this presentation. I'll talk a little bit about network event telemetry and some of the challenges with dealing with this as a data source. I'll discuss some simple techniques for dealing with those challenges. And when I say simple, I do mean simple, straightforward techniques. This is not going to be fancy statistical methods. These will be fairly straightforward, common sense techniques that unfortunately can sometimes be challenging to implement when you're in a distributed computing environment. I'll give you a quick refresher on Spark DataFrame functions, specifically window functions, because they make up a core component of the aggregations that I'll be describing later on in the talk. And ultimately, what I'm really here to talk to you about is this concept of dual window row count differential aggregations. And this is a fairly generalizable technique that will allow you to do some non-standard aggregations, or things that you don't think really within the context of MapReduce and how doing aggregations on that framework. Specifically, I'll walk you through two examples, the first of which is being consecutive event aggregations, and the second one being event refresh aggregations. And I'll discuss these in the context of evaluating and optimizing data processing prototypes. So first off, security ratings. Security ratings are an objective outside-in assessment of an organization's security posture built from externally observable data. This is modeled in a similar fashion to how credit ratings serve as a measure of financial risk. And unlike traditional security assessments, which are a point-in-time assessment where a report is generated, and that report is basically immediately stale. You may have some things to remediate, but a month down the line, 6 months down the line, how much value is that stale report now? Unlike that, security ratings provide a technique of continuously monitoring and measuring security performance. And this is used for a variety of different purposes. For instance, perhaps your company has critical vendors. You want to make sure if you're providing sensitive data to them or if you're giving them some sort of privileged access to your networks, you probably want to know that they implement good security diligence. And this is really the first use case of this third-party risk management. It's also used for a variety of other use cases, such as mergers and acquisitions, cyber insurance underwriting, and even security performance management. If your board wants to know, how well is our CISO doing, how well is our security team doing, security ratings provide an objective measurement of that performance over time. The way that these ratings are generated is I'm going to provide a very high-level overview of what is a very complicated process, but it really boils down to two separate processes. The first of which is generating this organizational digital asset inventory. And this is essentially the digital assets that an organization owns and operates. The separate process collects security event telemetry. We join those two data sets together, which allows us to attribute security events to specific organizations. And we feed that output into a security ratings algorithm that will allow us to regularly provide assessments of security posture over time. What I'm really going to focus on today, though, is this first piece of digital asset inventories and how they're created. And all digital asset inventory really boils down to is a collection of network identifiers. These can be things like IP addresses, domain names, attributed to organizations with a particular time frame. The challenge, of course, is doing this at scale across hundreds of thousands of organizations. And the way that these inventories are typically derived is through various data sets that provide observations of multiple identifiers that suggest some sort of relationship between those two identifiers. And the task at hand is to really take these data sets, infer which ones are accurate, over what time period are they accurate, and doing this, like I said, at scale, and generating something like this where we have a particular network identifier, in this case a domain name, attributed to an organization, BitSight, and the length of time that that's valid. Now, you may think that doesn't sound very hard or interesting, right? You have observations, you're just generating lifetimes, that's a simple aggregation. Well, that is easy if the data that you're consuming supports that particular use case. If your data sets represent the entire population of events, this is an easy task. If your events have birth events and death events, so you know exactly when associations start and die, it's fairly easy. And if you know that your data is robust, once again, this is easy. But no one wants to come to a talk and listen about how wonderful data makes data science really easy. So what I am going to talk to you about today is when this is not the case. When I want to infer these associations and when they're valid, when the data sets that I'm dealing with may represent small samples of the total event population, when many-to-many relationships may exist. So if I see an observation with a new observation or a new association, it doesn't necessarily age off any other association that may also still be valid. And of course, these factors really confound this problem and make it quite a bit more difficult. Now, I wouldn't want to use data sets like this to inform something like a security rating, which really needs to be robust and reliable. But nevertheless, I might be able to take advantage of data sets like this to help other use cases, such as providing enrichment information to our customers, where providing useful information in front of them that they can, they have the context to get rid of some of the ambiguity that me as a data collector or processor might not have. So the first challenge here, of course, is this notion of network event sampling. So when I say sampling to you, I have an audience of presumably data scientists, data engineers. You probably think of sampling in the sense of random sampling from a population and trying to make inference on the population based on that sample. If in the signal processing context, we think of sampling as regular periodic measurements of a signal. These are both desirable properties to have, but unfortunately, neither of them really apply in this network telemetry use case. If I'm collecting a network telemetry data set, it's probably, the events in this data set are probably emitted by some action. It could be a user action, it could be a protocol interaction, but in general, they're not going to be random and they're not going to be periodic. You're always going to have some sort of collection biases that is going to confound the inference that you're doing right here. So if you're looking at this data set, there's a couple things you need to keep in mind. First of which is applying domain knowledge. With some domain knowledge, obviously, if you're collecting events from a particular protocol and you have information of that protocol, you can apply that knowledge to help inform when lifetimes may exist or how long they may exist. You need to have some idea of what the sampling estimates really are. What the data set that you're consuming, the sample it is, make an inference as to how much of this is representative of the whole population. But really, most importantly, is use case. Some use cases, you can be really lenient. Some use cases have very strict false positive requirements, like the security ratings use case. But other times, you can get away with having sometimes messy or sometimes false negatives aren't actually all that bad. So really tailor the thresholding that you're going to do on these types of data sets to your use case. Second issue with network event data sets is this notion that network data sets often aren't very reliable. And this actually occurs probably more than you would think. This is especially the case in situations where you're collecting telemetry from a variety of sources and a variety of sensors that may be distributed across a network. But when you're processing the data in the end, you're losing that local context. You just have the aggregate results. So things that might be obvious at a sensor with that context may not be obvious when you're looking at the data in aggregate. A pretty common example of this that pops up in the news every now and then is this BGP example, where BGP, if you're not familiar, Border Gateway Protocol, it's a protocol that helps route traffic across autonomous systems on the internet. It's a peer-to-peer, point-to-point protocol, and there's no central repository for correct routes. You rely on peers to advertise them to you. And because of this, every once in a while someone fat fingers an autonomous system name, or sometimes organizations even maliciously change them in order to get traffic routed to places that they want. And as a peer in that network, you probably have a pretty good idea what the routes that you should see on a day-to-day basis. And we really rely on peers to filter that junk out. But of course, that's not always the case. Junk a lot of times get through. And if you're looking at this in aggregate, you may be a lot more difficult to weed out those sort of spurious associations as a result of either accidental or malicious action. A very trivial technique for dealing with this is if you're trying to extract associations from events or associations that may be spurious, is to simply require some sort of corroboration. Enforce thresholding where I have to observe this association multiple times before I'm going to say it's valid and assign it a lifetime. Obviously, this is going to reduce the recall of your data set, but if your spurious events are a relative minority, it'll help increase the precision. And it actually also has the second desirable property of reducing the jitter of the associations that you're going to be assigning over time. And what this chart here represents is there's a user logon data set where the blue line is generating associations based off of raw events, and the red line is associations that were corroborated by having multiple logins within a certain time period. And you can see there's a lot of flux in the raw associations. The associations that are corroborated provide a much more smooth, stable assignment volume over time, and that can be desirable if you're trying to make some sort of model or inference on that resulting data set. It'll be much more reliable. However, that brings up another issue. If we're going to require that events and associations get corroborated, we have to have some understanding of what is a corroborating event versus the event it is corroborating. We have to make that distinction somehow. And unfortunately, once again, in network telemetry data sets, this idea of doing proper deduplication can be somewhat of a challenge. As an example, if I go visit Databricks.com, a lot of things happen. Advertising trackers get loaded, support software, all sorts of things are going on. If the event I'm trying to model is me, Austin, visiting that website, and what I'm looking at is either web server logs or other network telemetry of all of these actions, what part of that telemetry represents the single event of me visiting that website? This can be especially difficult in situations where you're dealing with third-party data sets where maybe a lot of this is either anonymized or filtered out, or perhaps it's whittled down to only just a set of associations over time. Trying to achieve a good deduplication strategy can be very difficult if you're losing a lot of that context. However, if you're collecting some sort of event logs over time, you're almost always going to have a timestamp, or there will be some time element to it. So in the case where you really are struggling to find a good way to deduplicate these events, one thing that you can always rely on is time. And a very simple strategy for achieving this deduplication is to simply partition time up and leverage each time partition as its own deduplication key. And this works in the sense that events that co-occur are typically more likely to be somehow associated or closely aligned, but events are segregated in time. So I talked about some of the challenges here, and like I said, some simple techniques for addressing those. What I'm tasked with is really developing a data processing or a data processor that will work on one of these network event telemetry data sets, deal with some of the ambiguity with some of these techniques I described, and produce a set of associations with lifetimes. However, there's a lot of parameters that can go into this. How long are those time boxes going to be if I'm deduplicating based off of time partitions? How rigorous is my corroboration going to have to be before I make assignments valid? Or what is the corroboration window going to be? Ideally, I want to optimize all of these. Unfortunately, if you have a daily batch processor trying to do this on months of data, it can be extremely slow. Fortunately, this can be done in Spark with some creative aggregations to simulate the run of a processor that's implementing these types of techniques. Before I go specifically into how to do that, though, I'm going to give you a little bit of background on some Spark functions that are going to lead up to how to implement this type of aggregation. Just to get a survey, how many of you regularly use the DataFrames API in Spark? Good, most. One thing I was a little disappointed with the past couple, last year when I was here, is everyone always talks about the RDD API. And I'm a huge fan of the DataFrames API. I love it. You're going to hear a lot about it today. Hopefully, you'll be happy that some talks are focusing specifically on DataFrames. But DataFrames really provides two core functionalities, right? Built-in functions and UDFs where you can feed row values into a function and you get something out. And you get sort of a one-to-one mapping of input rows to output rows. And of course, you have aggregations, which you deduplicate on a set of keys and perform an aggregate across the values that share that set of keys. And this is a little bit different because you're fundamentally reshaping your data and calculating an aggregate. But one thing you can't do with either of these is maintain the shape of your data. Don't change the rows while calculating some sort of aggregate function across those rows. Fortunately, back in Spark 1.4, they added window functions, which provided a lot of really neat functionality. What window functions provide essentially are methods that you can define a relative grouping of rows or partitioning keys, and they provide a set of aggregate or analytic functions that you can apply within those windows. Very most simple example of this would be calculating a rolling mean where your relative windows or your relative rows are going to be some number ahead and some number behind of your current row, and you're just going to calculate, the aggregate is just going to be an average function. And you can see you maintain the same shape of your data, but you're achieving an aggregate on each individual row. However, there's still limitations here. There's only so many ways that you can define a window. It's basically based off of partitioning keys and relative row and value boundaries. So unfortunately, I can't use window functions alone to achieve the type of prototype simulation that I want to do. What I really need is these two types of aggregations. I need to be able to do consecutive event aggregations. And in this case, my data sets are typically associations of events. I want to aggregate across the events where there's only a single association observed. And anytime a new conflicting association pops up, I want to partition that aggregation into a separate aggregation. The second one is this concept of doing refreshed events. And this is where I want to do an aggregation across events that occur within a given time period. So if my time threshold is going to be 5 minutes, every time an event occurs within 5 minutes of a prior observation, those are all going to get smushed into the same aggregation. So the way that you can do both of these is this concept of dual window row count differential aggregations. And I think this is a fairly generalizable technique that you can do to achieve aggregations that you wouldn't traditionally think of in the MapReduce context. And the idea is relatively simple. And that's you have two window functions. What you're going to leverage is a differential function of the two row counts in order to generate some new partitioning key that is going to basically embody the context of whatever specific aggregation you're trying to achieve. And I realize this is very sort of abstract, and so I'll walk you through some specific examples of actually implementing this. First of which being consecutive event aggregations. So my first window is going to be essentially what my event keys are that I'm trying to do analysis on these associations. And I have a second window which includes another partitioning key, and that is going to be this key I'm going to generate that represents this event is not consecutive with the prior events. The new partitioning key I'm creating, like I said before, is going to be strictly a difference in the row counts of these two windows. And that will enable a new partitioning key that I can use to achieve the aggregation that I'm trying to do. So like I said, I'll walk you through a specific example. In this case, what I'm trying to do an aggregation on is how long is there only a single IPv4 address associated with a given IPv6 address. The first window in blue is going to be the v6 address. The second window is going to be the combination of these, both the IPv4 column and the IPv6 column. So the first row count, obviously, in this case, it just looks like a row count, and that's because there's only one IPv6 address. The second row count, obviously, is going to get split up when the second association shows up in the middle. And so what happens if I just simply take the difference in these two row counts, what happens is I get every time a new association pops up, the difference between these two row counts increments. And so it's going to end up splitting the aggregation up into only the consecutive events. So you can see with the first series, those get aggregated. The new association pops up. That's a separate aggregation. And then the third aggregation, which is the same keys in the beginning, gets split up into a third. Normally, in a traditional aggregation where you're just considering keys, this would only be two separate rows. But given the consecutive context that we're applying here, we can break this up. Doing aggregations like this is helpful for a BitSight where we're trying to identify how long are these associations valid. If I'm attributing an identifier to an organization based off some association, I need to know after certain periods of time, if I don't see that, what's the likelihood that that association is still valid? And these types of aggregations enable this type of study. So the second example, a little more complicated, the idea of doing aggregations with refresh. Once again, the first window I'm going to define is going to be my event keys. The second window is going to be the event keys plus this additional key, which I'm going to define, which is going to tell the ag whether or not the next event is within the given time threshold that I'm going to specify, or that's going to determine which events get aggregated together. I define this overlap flag as simply whatever the parameter I choose, 5 minutes, 10 minutes a day, whatever. You can use window functions to actually calculate that flag, and all you're doing is checking whether or not the next event is within that time threshold and applying the flag. The new aggregation key that I'm going to create is also, once again, a differential function of the row counts. However, I have to add a little bit of extra logic in here that is, it's only a difference in the row counts when there is an overlap. When it's not an overlap, I'm instead just going to use the second window row count, -1, which in effect is going to, whenever there is an event that is outside of the threshold and I'm partitioning the ag, it's just going to group it in with the previous ag. So once again, it's pretty abstract. Walk you through an example. In this case, I have an association of user login events, and I want to aggregate the events that occur within 24 hours of each other. So my first window is the IP column and the user column. My second window is those columns with this additional overlap flag, which, as I said before, is simply looking at the next event and saying, does this event occur within the time threshold, or should I split up my aggregation here? The first window count, the first window row count, once again, is just, looks like a row count, and that's because I only have one set of identifiers here. The second row count takes into account that overlap flag. And the differential function is going to be, like I said, the difference in the row counts when overlap's true. And it's going to be the second row count -1 in the case where it's false. And what you'll see there is essentially every time there's a false, that's incrementing the row count. And when we subtract by that 1 from that value, it's going to be whatever the prior grouping was. And so that just, every row that has a false, it's looping that event in with the previous aggregation. And what you'll see here is you now get separate aggregations that are split up by every time an event wasn't observed on a particular day. And you'll notice I have a count column here, and that's because I'm effectively counting how many days do I consistently see this identifier show up. And when I talked about corroboration and thresholding before, this is actually an easy way to accomplish that. Here I have my first grouping, I've seen an event across 3 days in a row, 1 day in a row, 2 days in a row. I can use that to achieve the type of thresholding that I was talking about earlier. So when I actually apply this to data, this is once again, a data set of user login events. I have the chart on the left, I have two lines, the blue being generating associations based off of no corroboration, and the red one being ones where I have some sort of corroboration requirement. In this case, it's did I see an event, or did I see a logon event at least twice within a given 7-day period? And obviously, what you'll notice is the lack of corroboration, the associations that are added on a daily basis is very high, and it's just consistently high. But when I filter out and only look at the associations that I've observed multiple times within a 7-day period, it's high in the beginning, and then it plummets. And what's happening here in this particular network is there is a large amount of shared lab machines. And so by trying to do the raw associations, including those shared lab machines, it takes up all the associations are people flipping between these lab machines. What I'm interested in is actually identifying what are the regular users that have fairly consistent usage patterns. Enabling this corroboration requirement helps filter out the associations that I'm extracting to only those that we see reliably over time. The chart on the right is the same data except a slightly different view of it. It is how many associations am I adding on a day that I have already aged off prior. And what you can see is without corroboration, this just steadily creeps up over time. And it's because we're constantly re-adding associations that we added and aged off because someone logged on a machine once. Maybe they use it 2 weeks, 3 weeks, a month later. So we're constantly revisiting those over time. Whereas if we have the corroboration requirement there, it's flat for almost the entire time because we're really only modeling the consistent regular users of the network. And everyone's probably wondering, why is there that big bump? And that's because that is the Thanksgiving and winter holidays where obviously nobody logs in and you're resetting. You're not seeing activity and it's getting reset. So with that being said, these aggregations, there's some scalability considerations that you want to keep into account. The first of which being, we're using multiple window partitions here. And so if you're doing partitioning on keys, you better hope they're not skewed. And I'm sure there's going to be a lot of great talks at this conference specifically on dealing with that challenge, but it's not going to be here. It's a difficult problem that we deal with in general in the Hadoop ecosystem. However, that being said, this particular use case where our events are associations of unique identifiers, typically you have a pretty, there's no skew in that frequently because they're unique identifiers. So it works really well for this particular use case. That being said, you are doing a lot of partitioning. There's going to be some shuffling involved. It's never going to be super fast. A great example of where this would fail miserably is if you were trying to do this type of aggregation on something that was, say, user agent strings to some other identifier. 95% of web traffic is within 10 user agent strings. Don't try and do this on user agent strings. It'll fail miserably. Second consideration that you should probably keep in mind is, when I first did this, my whole rationale for doing this was I had a data processing prototype, and engineering came back to me and said, hey, after we run this for 6 months, what is this data set going to look like? And I can tell you from firsthand experience, they really don't like it when you shrug. So I wanted to basically, in one batch, be like, I'm going to do one job. After 6 months, I'll show you what that data set looks like after this one job. And it was slow. And then it ran out of memory. And OK, I need to rethink this. And of course, the issue is, in this case, these window partitions are sort of agnostic of time. I'm aggregating over time. And so if the aggregation I'm looking at is over very long periods of time, and I'm partitioning on something that is ignoring that, I'm going to be getting very large partitions based off of data over time. One real easy way to fix that, though, is to simply do intermediate aggregations on smaller chunks of time. Not a big deal. A little bit of extra logic, but it will speed up the process quite a bit. And it's actually really nice, because with this particular methodology, the logic to do the aggregation and then the logic of re-implementing the aggregation on intermediate aggregation steps is actually the exact same. There is no separate logic. It is the same logic. You can treat a intermediate aggregated set of results as if they were the raw event data. So it's really easy to do. So with that being said, I discussed a variety of techniques to deal with some of the challenges of dealing with messy network event data. Specifically, we're leveraging Spark to do parameter selection, essentially, on a prototype, and ultimately inform engineering requirements. Because like I said, they do not like it when you cannot tell them how large a data set they're going to have to process is. Specifically, if you're trying to achieve these types of complicated aggregations where you're not exactly sure how to implement it, I'd really consider looking at this technique of trying to define some new aggregation key based off a differential function of multiple window functions. Can you use that differential function to generate the ag key that will capture the context that you're trying to accomplish in your aggregation? And finally, if you're running into scalability problems, consider an intermediate ag and compaction approach. It'll speed things up quite a bit. That being said, that was all I had, and I'm happy to take any questions. We still have about 9 minutes. Oh, thank you.